This is for class 12. Class 12. Today's topic is your moving charge in a magnetic field. Today's topic is moving charge in a magnetic field. Means moving charge, magnetic field. So first of all, let us consider a conductor. So first of all, so this is your today's topic is moving charge in a magnetic field. Charge in a magnetic field. So let us start with first is your magnetic force on a current carrying conductor. Magnetic force on a current carrying conductor. So let us see. That means from the topic there is a conductor. So this is a conductor. It is placed in a magnetic field. Say this is a magnetic field. Conductor, and it is of length L and length L. So instead of taking this B, let us take that, means this is kept in a magnetic field. So let us take like this into the plane of the paper. It is into the plane of the paper. This conductor is into the plane of the paper of length L, and say current I is flowing through it, because current carrying conductor, so current I is flowing through it. Let us take the charge density. Charge density is equal to N per unit volume, and this cross sectional area A, so your volume is equal to AL. Now this force, this is the force exerted by the magnetic field on the current carrying conductor. This is the force exerted by the magnetic field on a current carrying conductor. That will be Q V vector cross B vector. So V cross B. So here V, it is the velocity with which the conductor is moving, and this is the V, it is the velocity which is your charge, velocity with which the charge is moving, V, and B is the external magnetic field. This is the external magnetic field. So here this will be how much? F. So Q, that will be how much? Equal to Q N into AL. N into L, this much amount of charge, and this the velocity of the charge, means velocity of the electron is Vd, that is drift velocity cross magnetic field. So here you see that we are taking a conductor of cross sectional area A and length L, and current I is flowing through it, and it is placed in a magnetic field. This is magnetic field. It is towards into the plane of the paper. This cross means into the plane of the paper, because this is placed in a magnetic field. So here the charge, here charge means current is flowing through that. It is the velocity of the charge, that means the velocity of the electron, and it is the drift velocity. And you know that your current density is equal to I by A. You know this current density, And another thing, you know that I is equal to Q by T. So here your Q, that is number of charges, that is NaLQ by T. Here you find that I is equal to NaQ L by T. L by T, that is velocity. So I will be equal to NaQ, this is your drift velocity, L by T, this is your drift velocity. So this is your I. Now if you place here your current density will be how much? That will be NaQ Vd by A. So your current density will be NQ Vd. This is your current density. So this is your current density. So J, this is J. This is J, current density. Now what is your F? If you see minutely, this NaVd, that is current density, J, NQVd. So AL Vd cross B, this is your force. Now here you will see that your J is I by L. 1 minute, this Vd gets removed, because here you see, what you see here, that is NQVd, that is J. So it will be J AL Q cross B, this will be your vector. So now what is your now this is your force. So J is J into I is J. Here you say J into A. J into A is your current. So your force will be I force will be how much? High L. Where is the Q? Why Q is? Oh. See, your J is NQVd. This is your J. This is your drift velocity Vd. So when you place here, that is, it will be NQ. NQ. So NQ, here's your NQVd. This Q terms here, you can see here that NQ and Vd. Let me write it again here. There was a, here you can see that, you can see one thing, that is, what is J? What is J? So J will be, here you can see, this is J. So I is this much. So here J, area, this cancels out. So this will be N Q Vd. This is your Vd. I, this is your Vd. So here you see that in a force F, your NQ and Vd, this becomes J. So here it will be J vector AL cross B vector. This will be your, again J into A is your I. So F will be is equal to I L cross B. So here L is your vector, because what has happened here, that since I it is a scalar quantity and here it is cross, so we have to take L as vector quantity whose magnitude is L. So this is the force exerted by the magnetic field on this conductor. So this is your force exerted by the magnetic field on the conductor. So here what I want to tell you, that this I am dealing with only the important topics, so that these are the basics, and others are all these are, say, you have as you have studied in maths theorem, and corollary all are derived from this theorem. So I am dealing with the main topics. The main topics here, first is the magnetic force on a current carrying conductor. So here this is a conductor whose length is L and cross sectional area is A. So now I current is flowing through it and it is placed in a magnetic field. So what will be the force exerted by this magnetic field on this current carrying conductor? So here we have taken charge density, number of charge per unit volume, and V is equal to AL. This is your force Q V cross B. V, it is the velocity of the charge. Now Q will be total number of charge, that is NAL, NALQ. This is the total charge, and here the electrons are moving since current is flowing, so it is the drift velocity of the electron cross B. And you know that J is equal to I by A and I is equal to Q by T, so total charge is this much time. Now L by T, that is the velocity of the charge and it is the drift velocity. When you place here, your J becomes this much, and when you place this value of J in this, it will become this much. And we know that J into I is J into A. J into A is I, so J into A I. So here force, this is the force exerted by the magnetic field on a current carrying conductor. This is the force. So this is very important. Now my next topic will be, a charge is moving. Suppose a charge is moving in a magnetic field and the velocity of the charge is perpendicular to the magnetic field. That means, let the magnetic field, we have taken the magnetic field in downward direction. In the downward direction, we have taken the magnetic field in downward direction. So here what happens, downward into the plane of the paper. We are considering into the plane of the paper. We are considering into the plane of the paper. Magnetic field is into the plane of the paper. Now here see, this is the circle. Now here your velocity V of the charge is perpendicular to the, your velocity V of the charge is perpendicular to the magnetic field. So when it is perpendicular to the magnetic field, then a force, that is the centripetal force, that is the centripetal force, which that will be F, centripetal force F, that will be is equal to Q V cross B. This is the centripetal, this will act as a centripetal force, and this centripetal force will move the charge in a circle perpendicular to the magnetic field, in a plane perpendicular to the magnetic field, and it will move in a circular path. Now if this velocity B has a component, if this velocity B has a component along B, then that velocity has no effect on it, but the perpendicular component of V will move the charge in a circular motion, and the velocity V, which is in the direction, remember the velocity V which is in the direction of the magnetic field, velocity, that means the component of the velocity, component of V which is in the direction, component of V which is in the direction of magnetic field, that velocity will remain unaffected, and the velocity perpendicular and the component of V which is perpendicular to the magnetic field, and the component of the V, this is V, component of V which is perpendicular to the magnetic field B will move it into a circular path in a circle, and as a result the charge will move in a helical path. As a result the charge will move in a helical path. So here what is that? The charge, the magnetic field, it is inside the into the plane of the paper, and the charge V is moving perpendicular to B, and then the centripetal force, this is the centripetal force, because of this external magnetic field, it will move the charge in a circular path, and this will be in a plane perpendicular to the magnetic field. Now if the velocity component of the V is along B, magnetic field B, then that V will be unaffected, but the component of V which is perpendicular to B, component of V, this is in the direction of B, and another is the component of V perpendicular to the magnetic field. This component will form circular motion, and this component will be remain unaffected. So what do we find here? That the resultant motion will be a helical motion of the charge. So this is all about, that is, first of all, the very important point is that the force when acting on a conductor, remember that the force acting on a conductor carrying current placed in a magnetic field is equal to I L vector cross B vector. This is the force. Remember, this is very important. That is the force exerted by the external magnetic field when a current carrying conductor is placed in a magnetic field. Then the force exerted by the external magnetic field is I L cross, this is L cross B, I L, this is L cross B. So this is your force. And another important point is that if the charge moves with velocity V, if the charge moves with velocity V perpendicular to the magnetic field, then a centripetal force, this will be exerted, which will move the charge in a circular path and circular. If the component of V is in the direction of the B, then it will remain unaffected. This V will unaffected, but the component of V which is perpendicular to the magnetic field will cause a circular motion, and as a result the charge will move in a helical path. Now the next topic is Biot-Savart law. Biot-Savart law. This is an important law. That is, a conductor, say, here this is a conductor, and it is carrying a current, means current I is moving through it. Conductor current I is moving through it. So here I is moving through it. We are considering a small element dl here, and we want to know what is the magnetic field at point, suppose P. What is the magnetic field at P? So here we are considering this as the displacement vector. Remember, this is considered as the displacement vector, and the dl is making angle theta with r. So this dl vector is making an angle theta with the displacement vector. We want to know what is the magnetic field at P. What is the magnetic field at P? So according to Biot-Savart law, your dB is proportional to I dl cross r vector divided by r cube. Your magnetic field here will be how much? I dl means, see, I am writing it here, dB vector. Your dB vector will be how much? This will be I, current I, dl vector cross r vector divided by r cube. So here you see that if you applied right hand screw rule, so what happens? dl cross r. So your magnetic field will be direction into the paper. See, dl cross r. Here you see, this is dl cross r. You see my fingers, dl cross r. So it will be into the plane of the paper. So here your magnetic field will be this. This is the vector form. Now if you move to the magnitude, if you are going to move to the magnitude, you are going to, let us take dB vector magnitude, then what will happen? Oh sorry, this is proportional. One thing I have, this is proportional according to Biot-Savart law. So your dB vector, this will equal to some constant nu naught by 4 pi and I dl vector cross r vector divided by r cube. This is r, this is r cube. So this is what, this is your vector. Now if you go for magnitude, so this will be how much? This by 4 pi, here this is cross, so it will be I dl r sine theta by r cube. So this will be how much? This will be equal to, by 4 pi, your r cancel, I dl sine theta by r square. This is your magnitude and this is your vector. So do not confuse with it. This is your magnitude and this is your vector, and value of this, your constant, is 10 to the power of minus 7 Tesla meter per ampere. So this is the value of your constant. And so here this is the Biot-Savart law. According to Biot-Savart law, a current is flowing through the conductor. Here you see a current is flowing through the conductor, and now we are taking a small element dl, and we want to know what is the magnetic field at P, and this is the displacement vector. Your r is the displacement vector and theta is the angle between dl and r. So according to Biot-Savart law, that is your dB vector, that is the magnetic field at here, is proportional to I dl cross r vector by r cube. So your dB vector will be this much. This is your constant. And now if you take the magnitude, so your magnitude is this much, and this is your vector. Do not confuse with it. This is your vector and this is your magnitude. Now my next topic is the magnetic field on the axis of a circular loop, on the axis of a circular loop. So here you see this is your x-axis, this is your y-axis, and this is your z-axis. Now here this is a circular loop, and current is flowing through it. Now let us consider a dl element here, this dl element here, and another dl element here, here. Now we want to know what is the magnetic field at this point, and the displacement vector is your r vector, and from the center of the coil at this point your distance is x. Your distance is x. So here there is a magnetic field, say dB, magnetic field dB. Now it has two components, one along the x-axis, this is dBx, and another that is the perpendicular component dB perpendicular. So it has two components. Now it has been found what is the magnetic field. Magnetic field here is equal to 4 pi I dl by x square plus r square. This is the magnetic field at this point P. Now here what happens, the magnetic field along the your y-axis, the magnetic field along the y-axis, it cancels out, only the magnetic field remains along the x-axis. So your magnetic field along the x-axis will be magnetic field, this is along the x-axis, this will be how much, x-axis, nu 4 pi I dl into r, this is r is the radius of your circle, the loop, by x square plus r square to the power of 3 by 2. This will be your magnetic field, because here this is the magnetic field at P, but since it has two components along x-axis and perpendicular to the x-axis, so now what happens, that is the perpendicular component, all the perpendicular diametrically opposites perpendicular component cancels out, only the x-axis component remains. So here your magnetic field is this much. So your magnetic field will be Bx I cap, because along the x-axis. So your magnetic field, this is B I cap, it will be along x-axis. Now what is the most important point here, you see that your dl vector, this dl, your dl vector, it is in yz plane, it is in yz plane. Your displacement vector, it is in displacement vector, it is in xy plane, it is in xy plane, and your B vector is perpendicular, it is perpendicular, it is perpendicular to the plane formed by dl cross r vector. So this is an important point, your dl is in xy plane, your this r vector in this, where we are going to find the magnetic field, it is in the xy plane, and your dB vector, it is perpendicular to the plane formed by dl and r vector. So this is the magnetic field. Now if you want the magnetic field at the center of the loop, magnetic field at the center of the loop, that is, see, magnetic, if you want the magnetic field at the center of the loop, if you want to find the magnetic field at the center of the loop, then your B naught will be, that is x will be 0, so it will be by I 2r I cap. So this is very important, magnetic field at the center, this is very important, because it is used in any circular loop, it is used in it is used in any coil, solenoid, in any coil, what is the magnetic field at the center of the loop. So this formula is very important, this formula is very important. So here this is the magnetic field at the axis of a circular. This is the circular proof. At the axis you have to find the magnetic field. So here your magnetic field is this much, but your this is dB is this much. But what happens that your perpendicular component, which is diametrically opposite to the loop, it cancels out, only the x component remains. So your magnetic field along x component, that is the magnetic field along x, this is the magnetic field along x component, will be this much, and so your magnetic field will be, this is the magnitude into I cap. Now another important point is that magnetic field at the center of the loop, it will be how much? That is this much, because your x is 0. So this formula is very important, and you must remember it, because this formula is very important. It is always used in coils, especially in coils. Now your next topic is circular current loop. Circular current, this is R. Circular current loop as a magnetic dipole. Just now you have seen that your magnetic field in a circular loop, you have just now, it is I r square by 2 x square plus r square by 3 by 2. So here, if your x is very greater than r, so your magnetic field will be how much? I r square by 2 square cancels, r to the power of 3. So r cancels out. So this will be how much? X to the power of 3. So here B will be how much? Now we multiply by pi numerator and denominator. So this is area I into A by 2 pi x cube. So here you see again we multiply numerator and denominator by 2, so this will become 2ia by 4 pi x cube. This is 2. So here you see your Ia. What is Ia? Ia is equal to m, and this is magnetic dipole. This is magnetic dipole. So this will be how much? 2m by 4 pi x cube. So what, this is a very important point, that any current carrying circular loop, it is a magnetic dipole. What I want to tell you, that any circular current carrying loop, it is a magnetic dipole, and magnetic dipole I into area, this is magnetic dipole. So this is all about your important points in this topic. And remember that first of all, the most important point is that the force when a conductor when a conductor is placed in a magnetic field, what happens? The force exerted by magnetic field F is equal to I L vector cross R vector. This is very important. And next is that if a charge is moving in a magnetic field and the velocity of the charge is perpendicular to the magnetic field, then it will move in a circular path, and your centripetal force will be F is equal to Q V cross R, V cross B. That will be your centripetal force. And if the velocity component, if your velocity component is if a velocity component is in the direction of the magnetic field, then that velocity will be unaffected, but the velocity component which is perpendicular to the magnetic field, you will find that it will move in a circular path. So as a result, and this circular path, that is in a plane, this circular path, the plane will be perpendicular to the magnetic field, and as a result of these two component velocity, the charge will move in a helical path. And another important point here is the Biot-Savart law. This is very important. That is where this gives about when a current carrying conductor, we know that a current carrying conductor produces a magnetic field. So what will be the magnetic field at any point? So by the help of the Biot-Savart law, we can determine what is the magnetic field at some point, and it states that your magnetic field is proportional to IDL vector cross R vector by R cube. So this Biot-Savart law, we can determine the magnetic field at any point when a current is flowing through, when a current is flowing through a conductor. So this is very important. By the help of the Biot-Savart law, we are able to determine that if a current is flowing in a circular loop, then what will be the magnetic field at any point along the axis of the loop. And this we have, from here we got a formula that what is the magnetic field at the center of the coil, and this formula is very important because it is used in any coil, especially in solenoid. And so such type of questions has been asked in board as well as in competition. So this formula is very important. And your last topic is very important, that is the magnetic dipole. As you have early learned about electric dipole, similarly there is a magnetic dipole, and in which I have shown you that the magnetic dipole, it is equal to M is equal to I into A. I is the current, A is the area. So magnetic dipole, so in this the conclusion here is that any circular loop that is carrying current is a magnetic dipole. This is all about your topic. I have taken only the important points and taken the minimum time, so that it will be easy for you to revise and to revise the chapter.